Hello everyone, welcome to my YouTube channel, Usano-Goldie RL Marquez. In this channel, I'm going to upload a series of video presentations of lectures in differential calculus, integral calculus, and differential equations. In integral calculus, the main topics that I have chosen to discuss are as follows: basic integration, techniques of integration, definite integrals, applications of definite integrals, and multiple integration. The first video presentation of lecture that I'm going to tackle is about antiderivative of a function, which is under the basic integration in integral calculus. Let me now begin with my presentation. Basic integration, section 1.1, antiderivative of a function. Welcome to integral calculus, or calculus 2. Our main topic, basic integration. Our first series of lecture, antiderivative of a function. Integral calculus is a division of calculus that deals with the measure of the total effect on the net change of varying quantities. To deal with this net change, we need to understand the notion of an antiderivative or integral, its properties, and the methods of calculation. In differential calculus, we were given a problem about a function asking for its derivative or differential. This time, we do the reverse operation, that is, given the derivative or specifically the differential of a function, we determine a function called its antiderivative. What is an antiderivative of a function? A function denoted by big F is an antiderivative of another function denoted by small f on I if the derivative of big F with respect to x is equal to small f of x for every x in I. To visualize the relationship between the derivative and its antiderivative, the following anti-differentiation machine diagram illustrates how an antiderivative is obtained. The derivative denoted by small f of x enters the machine as an input. Inside the machine, it is trapped between the integral sign and the differential of x. The machine processes f of x, and when done, it gives a collection of functions as an output denoted by big F of x plus c. To understand this anti-differentiation machine further, let us consider the following functions. Big F of x equals x cubed, and small f of x equals 3x squared. Taking the derivative of big F, we get big F prime of x, which is equal to 3x squared. Since big F prime of x, which is equal to 3x squared, is also small f of x, then we say that big F is an antiderivative of small f. Let us have another function given by big G of x, which is equal to x cubed minus 3. Its derivative is 3x squared minus 0, which is simply 3x squared. This is also the small f of x. So we say that big G is also an antiderivative of small f. Let us have one more function denoted by big H of x, which is equal to x cubed plus pi. Its derivative is 3x squared plus 0, which is also the small f of x. So we say that h, that's the big H, is another antiderivative of small f. In fact, any function whose function value is given by x cubed plus c, where c is any constant, is an antiderivative of small f. The following theorem generalizes these observations. If big F is a particular antiderivative of small f on an interval I, then every antiderivative of small f on I is given by the big f of x plus c, a collection of functions where c is an arbitrary constant. To understand further the definition of antiderivative and the theorem that was just presented, let us have the following examples. If big f of x is equal to 2x squared plus x and small f of x is equal to 4x plus 1, then big F is an antiderivative of small f, since the derivative of big F of x is equal to 4x plus 1, which is also f of x. Moreover, 2x squared plus x plus c is the general antiderivative of f. Another one. If big F of x is equal to tangent 3x and small f of x is equal to 3 secant squared 3x, then big F is an antiderivative of small f, since the derivative of big F of x is equal to 3 secant squared 3x, which is also the small f of x. Moreover, tangent 3x plus c is the general antiderivative of f. Let us have one more. Let's suppose g of y, capital G of y, is equal to 3e to the y minus hyperbolic sine y, and small g of y is equal to 3e to the y minus hyperbolic cosine y, then the big G is an antiderivative of small g, since the derivative of big G of y is equal to 3e to the y minus hyperbolic cosine y, which is also the small g of y. Moreover, 3e to the y minus hyperbolic sine y plus c is the general antiderivative of small g. Last, let's say we have big H of s, which is equal to ln of 1 plus s squared minus inverse tangent of s, and small h of s is equal to 2s minus 1 all over 1 plus s squared. Then h is an antiderivative of small h. So big H is an antiderivative of small h, since its derivative, the derivative of big H of s, is equal to 2s minus 1 all over 1 plus s squared, which is also the small h of s. Moreover, ln of 1 plus s squared minus inverse tangent of s plus c is the general antiderivative of h. From the definition of antiderivative and the theorem that was presented together with the examples discussed, we have the following process called anti-differentiation or integration. What is an anti-differentiation or integration? It is the process of finding the set of all antiderivatives or integrals of a function. Indefinite integrals. The general antiderivative of small f is also called the indefinite integral of small f, and we write the indefinite integral of small f of x dx is equal to big F of x plus c. In this relation, this elongated s is the integral sign. Small f of x is the given derivative or the integrand. The differential of x, denoted by dx, indicates the variable of integration. C represents the arbitrary constants of integration. Big F of x, a particular integral or a particular antiderivative. Big F of x plus c, the indefinite integral or the general antiderivative. Let us have the following examples. The following are indefinite integrals. The integral of 3x squared dx equals x cubed plus c. Here, f of x, small f of x, is equal to 3x squared, while the big F of x is the x cubed. Second, the integral of cosecant squared x dx is equal to negative cotangent x plus c. Here, the small f of x is equal to cosecant squared, and the big F of x is equal to negative cotangent x. In the first example, if you're going to differentiate big F of x, we get this integrand. In the second example, if we're going to get the derivative of negative cotangent x, that is negative of negative cosecant squared, so we have positive cosecant squared x, which is the integrand. Integral of 5 e to the 5y dy is equal to e to the 5y plus c. If I'm going to take the derivative of this, we have 5 e to the 5y. Here, f of y, small f of y, is equal to 5 e to the 5y, the integrand. Capital or the big F of y is equal to e to the 5y. Taking the derivative of this, we get 5 e to the 5y. Let us have this part for example. The integral of dw over 1 plus w squared is equal to inverse tangent of w plus c. Here, small f of w is equal to 1 over 1 plus w squared, while big F of w is equal to inverse tangent of w or arctangent of w. If I take the derivative of this, I will get 1 over 1 plus w squared. In number 5, this integrand is the small f of t, while this is the big f of t, which is ln of t squared plus 5. If I take the derivative of this, I get the derivative of the expression inside ln, that is 2t plus 0, simply 2t, over the expression inside ln. Number 6, the integral of hyperbolic sine z dz is equal to hyperbolic cosine z plus c. Here, small f of z is equal to hyperbolic sine z, while the big f of z is equal to hyperbolic cosine z. The derivative of hyperbolic cosine z is equal to hyperbolic sine z. Consider the following indefinite integral. The expression ln x plus 2 quantity to the fourth times 1 over x is the integrand, and the variable of integration is x. In evaluating indefinite integrals, the following theorems are found useful. Suppose f and g are functions defined on some same interval and k any constant. Then the following 4 properties hold. The first property, we have integral of the differential of f of x is equal to f of x plus c. So notice that if the integral sign and the differential operator are next to each other, they disappear, leaving only this expression or this function f of x. If the integrand f of x multiplied by a constant k, this constant k can be moved out of the integral sign. So hence the integral of k times f of x dx is equal to k times the integral of f of x dx. If in f of x, x is multiplied by k, then the integral of f of x, the integral of f of kx dx is equal to the integral of f of kx multiplied by k dx, but it is multiplied outside by its reciprocal. Multiply inside by k, we need to multiply the integral outside by 1 over k. If we have the integral of a sum, it is equal to the sum of integrals. General property number 4 can be extended to more than 2 functions. So if u sub I is equal to f sub I of x, where I is equal to 1, 2, 3, and so on up to n, then this property holds. So, example, the following integrals illustrate property number 1. The integral of the differential of x, since the integral and dx are next to each other, then we simply have x then plus c. Number 2, we have integral of differential of y cubed. So again, since the integral is next to each and the differential is next to each other, then we say that this is equal simply to y cubed plus c. Third, we have the integral of the differential of 5e to the z. So these operators disappear, giving only 5e to the z plus c. Property number 2 or property 2 is illustrated by the following examples. Integral of 3 multiplied to 5x cubed plus 1 quantity squared. Since 3 is a constant, I can move it out, giving 3 integral of 5x cubed plus 1 quantity squared. If I have integral of 2 sine cube w dw, again, this 2 is constant, I can move it out, giving integral of sine cube w dw multiplied by 2 outside. Property number 3 are illustrated by the following examples. The integral of e to the negative 3x dx is equal to the integral of e to the negative 3x. I'm going to multiply inside by negative 3, and then I'm going to multiply outside by its reciprocal, negative 1/3. Given the integral of secant squared 5z dz, so again, I'm going to multiply this by 5 inside, but I am going to multiply outside by the reciprocal. Property number 4 are illustrated by the following examples. Number 1, integral of x squared plus e to the x over 1 plus e to the x quantity dx. This gives us the integral of x squared dx, meaning integral of the first term plus the integral of the second term. If we have 3 terms inside, so the integral of this is equal to integral of the first term plus negative integral of the second term plus minus the integral of the third term. Let us consider another example. If the integral of f of x dx is equal to x cubed plus c, what is the value of the first derivative of small f when x is 2? To find the value of f prime of 2, so we need to get the derivative of this function, the first derivative. By the definition of antiderivative of a function, small f and the big F, which is this one, are related by this equation. Small f of x, the integrand, is equal to this particular integral or antiderivative. So this is equal to x cubed, which is our f of x, big F of x. Since the two are related, f of x is related to f prime of x, big F prime of x, let's get the derivative of this. Getting 3x squared. So big F prime of x is equal to 3x squared, so that is equal to small f of x, from which we can now get its first derivative, which is 6x. So getting the value of f prime of 2, small f prime of 2, we have 6 times 2, which is equal to 12. Therefore, f prime of 2 is equal to 12. We can solve this by another method. Let's consider this integral, which is equal to x cubed plus c. Taking the derivative of the left and derivative of the right separately, we have derivative with respect to x of this integral is equal to the derivative of the right side. But this gives us simply f of x, while the right side 3x squared plus 0, which is simply 3x squared. Since we know already f of x, which is equal to 3x squared, we can now determine its derivative, which is 6x, from which it follows that the value of this derivative when x is 2 is 6 times 2, which is equal to 12. Therefore, f prime of 2 is equal to 12. Let us have another one. Example 1.1.11. If the integral of f of x dx is equal to 1/4 x to the fourth minus x cubed plus c, what is the relative minimum point of this function, small f of x? By definition of antiderivative of a function, again, f and big F are related by this equation. F of x, small f of x, is equal to the derivative of this big F. In this relation, this is equal to the big F of x. 1/4 x to the fourth minus x cubed. Taking the derivative, we get 4 times 1/4 using our formula for differentiation. 4 times 1/4, so that is 1 times x. 4 minus 1, that is 3, so we have x cubed. While this one, so minus 3x squared, again by simple power formula for differentiation. This big f prime of x is equal to f of x. So f of x is equal to, small f of x is equal to 3x cubed minus 3x squared. Getting its derivative, we have 3x squared minus 6x. To determine the relative minimum point of f, we need to find first the critical points. To determine the critical points of f, we're going to equate the first derivative, its first derivative, to 0. So 3x squared minus 6x is equal to 3x squared minus 6x equals 0. We can factor out 3x, giving 3x multiplied to x minus 2. This is a quadratic equation. Equating its factor to 0, we have 3x equals 0 or simply x equals 0. The other factor we have, when equated to 0, x minus 2 equals 0, gives us x equals 2. So x is equal to 0 or x equals 2. To solve for the corresponding points, we use this f of x, which is equal to x cubed minus 3x squared. When x is 0, so we have f of 0. So y is equal to 0 cubed minus 3 times 0 squared, which is equal to 0. Hence, we have a point 0, 0. When x is 2, we have f of 2. So 2 cubed, plug it here, plug it in here. 2x cubed minus 3, 2 squared. So we have negative 4. So this is 8 minus 3 times 4. This is 12. So 8 minus 12 equals negative 4. Hence, we have 2, negative 4 as a point. Therefore, the critical points, we have 0, 0 and 2, negative 4. Which of these 2 points is a relative minimum point of f? So let's see. The derivative of small f of x is equal to 3x squared minus 6x, as what you had here. its second derivative is 6x minus 6. In differential calculus, applying second derivative test, we have the following. If the second derivative of f of x is greater than 0, then the critical point is a relative minimum. If it is less than 0, it is a relative maximum. When x is 0, the second derivative is 6 times 0. So 6 times 0 minus 6 equals negative 6, which is less than 0. So hence, this is not what we want, because what we want is a relative minimum point. Therefore, we want our second derivative to be greater than 0. Let's try the second one. When x is 2, the second derivative of f is 6 times 2 minus 6. So 12 minus 6, so that is 6, which is greater than 0. Therefore, the relative minimum point of f is 2, negative 4. This critical point. By the way, 0, 0 is a relative maximum point. Again, the relative minimum point of f is 2, negative 4. Let us have this last example. If the integral of f of x minus 2 dx is equal to ln of x squared plus 1 plus c, what is f of x plus 1? Also, solve for x in the equation f of x plus 1 equals negative 1. By the definition of antiderivative of a function, again, small f and capital F are related by f of x small f of x is equal to f prime of x. Let us consider this left side in this relation. That is equal to ln of x squared plus 1 plus c. This implies that capital or big F of x minus 2, because this is small f of x minus 2, therefore this expression is equal to, or this function is equal to capital or big F of x minus 2, which is equal to ln of x squared plus 1. Now from this, we can now determine the big F of x. To determine the big F of x from here, we replace x by x plus 2. Replacing x here by x plus 2, we get ln of the quantity x plus 2, quantity squared, plus 1. So again, we replace x here by x plus 2. If we want to solve for f of x, knowing that f of x minus 2 is equal to ln of x squared plus 1. By the way, small f and big F here are related by f of x, which is equal to f prime of x. From here, we can now solve its derivative. The derivative of big F of x is equal to derivative of the expression inside. So that is 2 times x plus 2 quantity to the first using general power formula. So drop the exponent, copy the base, subtract 1 from the exponent, giving 1. All over, because this is logarithm, natural logarithm, its derivative is derivative of the expression inside over this expression. So again, the derivative of this is 2 multiplied by x plus 2 all over this expression. Simplifying the denominator, expanding the denominator, we have x squared plus 4x. This is 4, x squared plus 4x plus 1. So 4 plus 1 gives us x squared plus 4x plus 5. So big F prime of x therefore is 2 times x plus 2 all over x squared plus 4x plus 5. Solving for small f of x, so we have 2 times the quantity x plus 2 all over x squared plus 4x plus 5, because small f of x is simply big F prime of x. Now from here, if you want to solve for small f of x plus 1, so all you have to do is to replace x here by x plus 1. So getting 2 times, so this is x plus 1 plus 2 all over, so this is replaced by x plus 1. So quantity squared, 4 times x plus 1, then plus 5. Simplifying, we get 2 times x, which is 2x. This is 3 times 2, 6, giving 2x plus 6 in the numerator. In the denominator, if we expand this gives us x squared. So let's have it here. So this is x squared, then plus 2x plus what? Plus 1 plus what about here? That is 4x plus 4, then plus 1, plus 5, sorry, plus 5. So we have x squared, so this is x squared, 2x plus 4x, that is 6x, 1 plus 4, 5 plus 5, giving 10. So the denominator is simply x squared plus 6x plus 10. Therefore, we're done. So small f of x plus 1 is equal to 2x plus 6 all over x squared plus 6x plus 10, which is what we want. So this is what we want, and so we're done with this. What about x in the equation of f of x plus 1 equals negative 1? To solve x in this equation, we replace this by its equivalent, which is 2x plus 6 all over x squared plus 6x plus 10. So this is what we have, which we got here. So that is equal to negative 1. Multiply its side by this denominator of the left side. We get 2x plus 6, negative 1 times this denominator of the left side. We have negative of x squared plus 6x plus 10. So this is, when transposed on the left side, is x squared. So this is 2x plus negative 6. So 8x, negative 10. So when transposed is positive 10 plus 6, negative 16, equal to 0. So this is a quadratic equation which is factorable this left side into x plus 4 quantity squared. So that is equal to 0. The root of this equation is x equals negative 4. So therefore, x equals negative 4 in this equation. So we're done with the second question. So thank you for watching. Please don't forget to subscribe at my YouTube channel, Usano-Goldie RL Marquez. And for the next video, lecture notes to general power formula for integration. Bye!